My name is Guhy. Moving on into ceramics, I'll be talking today about barium titanate. The study was done by some guys at UTEP in Texas called the fabrication of barium titanate by binder jetting additive manufacturing technology. Basically, the study is on the feasibility of barium titanate as a piezoelectric material, and also not just how well it works in that application, but also how well it can be additive manufactured through this binder jetting process. And then one of the main, process conditions that they varied was the sintering temperature. So how does the sintering temperature affect these piezoelectric properties of the material? So like I said, it's barium titanate. There's a chemical formula for it. The top diagram there is kind of the binder sintering diagram of this machine. Has a powder on one side. I don't know if we've gone over that or not, but powder on one side, and then the deposition side on the other. Basically, just rolls the powder over, and then this binding agent is lasered in and then sintered. They used a lot of different. So not only did they vary the sintering temperature, but a secondary test that they did was to vary the binder saturation, and that kind of gave a preliminary test as far as which percentage it was going to give the best results and the highest densities. And I'll go over that in a second. They used a lot of different analysis techniques in this study, just to kind of, like I said, the production side. I feel like a lot of studies have a lot of different, they have a lot of different runs and they print a lot of different samples. This one printed very few samples and did a lot of different analysis techniques on those samples. They did SEM, scanning electron microscopy. They did some X-ray diffraction. The TGA is like a gravitational analysis. They took digital calipers just to measure the geometry to make sure that there was no deformation. And then they also did vector network analysis, and that was more of to get the electrochemical properties. The second diagram at the bottom there shows the sintering process, how they did it for each different materials. They did 3 different temperatures, as you can see on there's a laser. Yeah, 3 different temperatures there. And then this is kind of how they sintered it over time. So the first hour and 20 minutes, it went up and stayed at 600 degrees, and then they took it all the way up to its max temperature at a steady rate. And then once they reached the max temperature for the setting, they would walk it down every hour or so, just to give it that entire sintering process. The first study, actually I'm going to skip the second one because this one it's kind of the secondary study. It's not as important, but they did it first. This is where they varied both the sintering temperature, as well as the binder saturation. They used both variables to kind of see what worked better. And in this study, they kind of realized that 60% binder saturation is what they wanted to go with. It gave the highest density for the product, which is what you want, which is what you kind of want. This diagram here is some SEM photos of. It kind of illustrates. This is the more zoomed in, but basically, as that binder is, forms the part, and then as it is sintered, the binder evaporates or dissipates and leaves these holes behind, and that's what causes your density, your low densities if you have a lot of binder saturation in the mix. So they went with a lower binder saturation to keep these holes as small as possible, keep the density high, that way to improve the electrochemical properties. And then again, the sintering temperatures here, as you can see, the sintering temperature, the lower the temperature, the higher the density. So that kind of gives a little, foreshadowing into the next study, which was, how ultimately does the sintering temperature affect the piezoelectric properties. So here again, you can see the higher the sintering temperature, the higher this is the dielectric constant, which is one measure of how well these materials are going to work as semiconductors and their electrochemical conduction. This is a loss, and it's kind of gives similar. Basically, the lower temperature here has the highest loss. And then they did multiple analysis techniques to prove the same thing. They had They had a graph for dielectric constant as well as a graph for. I don't think I used it. Yeah, this is the XRD. I'll talk about that in a second. And basically, the reason they did a lot of SEM and XRD to kind of not only understand the fact that a higher temperature gave it better properties, but why does it give it those properties? And here are some SEM photos. You can see will be your low temperature, this will be your high temperature, and then your middle temperature, and then your highest temperature. And this is a zoom out shot and a zoom in as well. These are all the same. These are the same magnification. These are the same magnification. So you can kind of see at the lower temperatures you have a lot more gaps in your material, and then as you get to the higher temperatures, it becomes a lot more dense. And you can understand how that would affect it and cause better conduction and better electrochemical properties in this material. So this higher temperature, you can really see it becomes a more unified, solid material through that sintering process, and becomes a lot better of a semiconductor and a piezoelectric material. So this is pretty much the main reason why they're saying that these properties are occurring. They also did some X-ray diffraction, which kind of gives some hints at the chemical or the crystal structure of the material. I didn't really understand exactly how this played into to the conclusion, but they did do it, and they did give data on it. And then, as you can see here, I think the hexagonal was the main form of the crystal structure that they were finding. In summary, the study did prove that the barium titanate is a very good piezoelectric material, and it shows a lot of potential for the additive manufacturing side because it was very easy to print. They didn't give any graphs or anything, but basically I said they used digital calipers to measure the geometry. Basically, they didn't have a lot of variance in deformation of the part from different sintering temperatures. They pretty much got a very steady size of the part. The only thing that was varied was the density and the properties. So it looks very good for the additive manufacturing side. Very easy to print, not a hard process at all. And then the binder jetting process can be manipulated pretty easily to increase or decrease certain properties. Very simple. What I thought about the research, I thought it was very straightforward to the point. There wasn't a lot of extra, writing and extra data and extra graphs that didn't have any use. It was kind of, here's our very simple hypothesis at the beginning. Here's how we did it. They explained the printing process and their analysis techniques, and then gave